Hi, everybody, LRVS, and with that very dramatic minute countdown, I am very, very honored to introduce you to Shane Turcott. He is the principal I'm going to mispronounce this, the principal metallurgist at Steel Image. Shane will be there for the Q&A, so he can help me pronounce that word. Principal metallurgist at Steel Image, and Shane will be presenting the enigmatic title, RCA Starting with the How. You can find out more about Shane and connect with him in the speaker profile. And also on the lower left, I am going to introduce Shane's code, if I can get that up. And let's get started with this presentation. And I just want to remind everybody, in the cropping of the video, there might be several seconds of a little downtime, just several seconds. Patience, please.
Hello, LRVS. It's very exciting. My name is Shane. I'm very excited to be here today. But I guess because this is a recording that I'm making near Toronto, Canada, that I'm technically not there, nor is it today. But I am sure that Shane, the future Shane, who's waiting to answer all your questions at the end of this, is very excited and will be there. I will be there to answer questions at the end of this. Now, because it's a recording, I'm not quite sure how much I've been introduced. So let me introduce myself. I am a metallurgical engineer that started an engineering company called Steel Image. Although I'm not a reliability engineer, the vast majority of my work is supporting reliability efforts. Steel Image, we use lab-based equipment to provide as much information as possible from parts. Predominantly what I do is when equipment fails, by getting more information that would not otherwise be obvious, we can provide more details useful to explaining how and why equipment has failed. I think the reason why I'm here today, and I got the special mention, is that I wrote a book called Decoding Mechanical Failures. It is intended to share the information of how to examine and interpret mechanical failures to any engineer, including reliability mechanical engineers. And I also want to say that it's also a really good book in the sense of not only does it teach you how to diagnose, to recognize and diagnose how something's failed, is how do you then use that diagnosis in the remainder of your RCA, and how does that lead you directly towards the root cause of failure? I've also started doing online training, and when COVID is over and it permits, I will, as soon as possible, go back to in-person training. But bear in mind that my primary interest is actually doing the failure myself. Over the years, it's been pretty exciting. We've grown a really reputable client base, and here are some of the companies you might recognize. Now, I think everyone here intuitively understands that things can fail for a variety of reasons, and each of these reasons and what we'll call failure modes occur for very different reasons. and they require very different solutions. Just, obviously what causes fatigue and what causes brittle fracture, or what causes one of the many corrosion-based mechanisms is going to be very different, and how you would investigate, fatigue, brittle, or corrosion-based is very different, and then the solutions that you would have to apply to ensure that no other parts fail in the same way are all going to be incredibly different. And which is why when we're doing an RCA or any reputable investigation, we have to begin with understanding how the part failed. And I appreciate that when we walk into these scenarios, that there are some techniques, such as like the 5 whys, that they first ask the question, why did the part fail? But if you don't understand how it failed, the premise of this talk is that you'll never get to explain why it failed. And so only once we understand how it failed can we begin, or an investigation begin, to understand why it failed. To diagnose how a part failed, that can only be done by examining the failed part. I appreciate that, again, reliability engineers or rotating engineers or a lot of mechanical failures will do the very best that they can to get as much data as they can from around the failed part, vibration, histories, and that kind of stuff. But until you actually examine the broken part itself, you're always going to be a little bit of guesswork. And maybe a morbid analogy that I've used in the past would be like, imagine a murder investigation where they examine everything in the room, but they don't actually examine the murder victim, like the actual body of the murdered victim. And so to really know how a part failed, you have to examine the broken part itself. And for many failure modes, that includes examining the fracture surface itself. That different fracture features, they represent different things, and that can be interpreted. And I'd like to demonstrate how this is done, and the importance of identifying the details of how it failed, the failure mode, where the crack starts from, and such, and how that's really important to an RCA. Or phrased differently, if you don't do it, would you have guessed what the root causes were to each of these 3 chain link failures? Okay, so why are we doing chain links? Well, a couple of reasons. Number one is that they're very simple items that I think everyone here everyone from very different industries can look at it and go, I conceptually understand how they work. And then hopefully people can conceptually understand how important they are. These are from automotive assembly plants that people will sometimes, depending the line, will go in between vehicles to assemble them, to put things on, to mount them. And so when these break, they represent a massive safety issue that could effectively, I've always kind of pictured it as like the domino effect, is that everyone goes in between the vehicles, and if it breaks, everything shifts a little bit, you dominoes a whole bunch of people, and that's not desirable. But also there's a lot of money at stake. When these break, they lose production time, they cannot get back, and we're talking fractions of millions of dollars. And of course, there's going to be time and replacement costs to replace it, depending what solutions are deemed necessary to it. So example number 1, a failed chain link. This is from an automotive assembly plant. They suffered 2. The chain was 15 years old, and they had never had failures before these 2 links. But 2 years ago, they did make modifications to the line. They had included additional bends and turns into it. Now, again, the only way to be sure how something failed is by examining as fracture features, and that requires a knowledge of what to look for. In this case, what we see is that it is a fatigue failure, and that it's what we call a low cycle fatigue failure. Phrased differently, it is a fatigue failure from many cycles, but the loading on it was extremely high. When we look at the initiation site, so we have to again pick out where the crack starts from, is we don't see any features that are unusual or unexpected at that initiation site to make us suspect that there is a problem in manufacture or materials at that point. So how did the part fail? Well, it failed by fatigue, which means that the level of repetitive loading was above the fatigue limit or durability of the link. That does beg the question if the durability of the link was what it should be. And so instead of guessing what that is, a little bit of extra testing, you can assess whether the link was what it should be. So is the chemistry, hardness, strength, and microstructure in this case are all fine. We can come back and say, hey, your link is there's no quality issue, and you guys broke a perfectly good link. Going back to our logic train, that means that we have a fatigue failure, which is caused by the repetitive loading, which is above the durability of the link, but my link is okay. And so through elimination, that now means that we know that this link failed because the loading on the line was too high. And that now allows the remainder of the RCA of the investigation to focus on, hey, why was the loading higher than it should be? Of course, one of the, in this case, one of the key suspects was that if it'd been operating for 15 years, no trouble, but 2 years ago you modified it, you're going to start looking at what were those modifications to the line, in particular bend radii, and the line tension that was applied afterwards. Now, knowing this and figuring out that the link had been overloaded, it's really crucial to preventing future failures. Now that we know that this link had suffered higher loading than expected, what are the odds that only this one link had? And it's probably very low. And so that means that the majority of your, essentially all of your chain has probably been overloaded, and there's a strong likelihood that other links in your chain has been cracked. They already have fatigue cracks in there and they're just growing. It's going to be a matter of time. And so to solve this problem, you need to do two things. And the order of doing this is incredibly important. You need to first figure out how to reduce the loading on the chain links. So you have to go and investigate where the extra loading is coming from and mediate that. And then secondly, you have to then replace the chain because there's probably links in there that are already cracked. If you get the order wrong, it's a ticking time bomb again, and you're gonna have failure. If you replace the chain link, before reducing the loading, you could create additional cracks and cause failure again. All right. Example number 2. Now this was another automotive assembly plant. This chain was a new chain and had been installed 2 years beforehand. Now, when we look at the fracture surface on this one, because again, the only way to be sure how something failed is by examining the part itself, is that we come back and yes, it is fatigue cracking, but but you'll notice here quickly that there's something that looks very different about this fracture, and that is because a third of the fracture surface is actually a forging flaw. And so how it failed, well, I mean, first of all, it actually started to fail during the forging process. It began to tear. And then later on, when you actually put it into service, it took 2 years for a fatigue crack to grow from that forging flaw and cause failure. So why did it fail? Well, simply we can use the knowledge to say, okay, well, repetitive loading was greater than the strength of the part, but I already have a pre-existing crack-like flaw in there, which acts as a stress concentrator. So I can explain why the loading on this link was higher because of that flaw that is in there, which means that it's less likely that you have a setup issue, and instead your failure is associated with a quality issue with that link itself. And now when you assess what your risk is with the rest of your line, your risk is going to be not about whether your line has applied loading to every part. You're going to be assessing the risk of what is the risk that other links in that chain have the same flaws as this and such, okay? So already between the first and the second, the root cause is incredibly different, and your solutions are going to be also incredibly different. And I mean, if you didn't examine the two parts, I think it would have been very challenging to figure out which would have been the right path. But we have a third example to complicate this and show again how important it is to understand how. So this one, we have a dollar sign. So they reported this failure occurred over 10 years ago. That when this happened, they lost about $250,000 in lost production. Again, they had safety concerns because a lot of people work on this line. It was their main assembly line, and so yeah, dozens of people could have got hurt. And so management came back and said, you cannot allow this to happen again. You have to figure out how to solve this. So some people sat around and said, hey, it's a 20-year-old link chain. Let's just replace the entire chain, and hopefully that will solve the problem. but you know, because it was a big RCA, they actually went and did the effort to try to understand why it failed. And here's what we found. So when examining the failed link, what was found was that the fracture appeared very different from fatigue. Again, because the fracture features that form, especially in mechanical failures, how it forms creates different appearing fracture features. And that's the whole point of what we call fractography, is being able to examine the fracture surface of failed parts. And in this case, instead of looking like fatigue, it actually looked like it was brittle. And so in our first assessment is that it looks brittle. Doing a bit more testing, we come back and we found that yes, it was in fact brittle. So when we tensile test it, which should be a relatively ductile material, is that it can't sustain any stretch. Once it stretches even 2%, boom, it breaks. And it broke in a brittle manner. So now we can identify the how it failed simply as it was brittle. And it was brittle because the material itself was embrittled. And that embrittlement had happened 20 years ago when they first made this chain link. Which means that, again, now we're starting to get into the RCA of as to why it failed. Okay, and that's going to continue on. But you know, to start that process, we now know it's brittle. It's brittle. The material is brittle when it was made 20 years ago. A little outside the scope of this simple presentation, but for those who are really interested, it's tempered martensite embrittlement. And then secondly, if a part's been brittle for 20 years and it hasn't broken, it does mean that the loading has changed on it. Something has hit it in a new way, or it's been strained in a different way. So there's still the investigations we have to figure out where that elevated loading has recently come from. And you are going to assess that other links produced at that same time or in that lot are also going to be at risk in the same way. Now, again, I mentioned that this work was done some time ago. The plant was able to use some geometrical differences of the links of that time, and were able to sort it out from their line. And they actually found that there was a very low number of links in their line. And since they were able to sort those out, they have not had a failure in the past 10 years. And there you go. My key message from this talk is that if you want to know why something failed, and you should, when something breaks, you want to understand why it failed, but you can only do that once you know the details of how it failed. And by details, I mean, what was the failure mode? Where did the crack start from? And other things relevant to the mechanisms and how it failed. You can only understand how something failed by examining the broken part. And if you think about it, it just makes so much sense. The broken part holds the most amount of information as to why it broke. And although a lot of times in the past, people have not been able to, you know, at least have the ability or the skills to examine the broken part, and are doing the very best they can with whatever data they have from around it. They really, I'd like to change the conversation and say that it is possible to examine the broken part, and that can be done. That can be learned how to be done, because once you know how a part failed, the conversation that occurs next is actually very natural, and it directs an RCA towards why it failed. In the case of the chain link that failed by fatigue from really high loading, the question is going to be, well, you know, first question is going to be like, well, if it's the loading was greater than the strength, the durability of the part, let's figure out which of that is, you know. So like let's do some quick testing to make sure the link was of good quality, and then the question is going to be, okay, well, where did that extra loading come from? And now the investigation is going to focus on where that extra loading came from. Versus if in scenario number 2 you have a forging tear, you're going to have a quality issue. You're now going to be less concerned about the excessive loading. You're now going to be focused upon the quality of it and what's your risk of other parts. Or if it's embrittlement, you're going to have some slightly different questions, but again, following that process. But the conversation as to why it failed, which at some point I think will eventually turn into human factors and such, but at least it's in the right direction and you're not making mistakes. In the end, it's really too important to guess how something failed, especially if there's safety critical or there's lots of money involved. And so to understand how it failed, you've got really 2 options. And essentially it's who analyzes, who examines the broken part. Option number 1 is that you can have it analyzed by a laboratory. That's what I do all day long. And it is my highest recommendation. With additional lab tools, you can get the most amount of information from possible. But I want to emphasize option number 2, which is still a really good option. And that is that reliability engineers or frontline workers who are dealing with and seeing the broken parts, they can learn to examine fracture features, the very basics at least. And so I think that should be mandatory for anyone doing lots of RCAs or leading RCAs, to be able to look at broken parts, because there's going to be many times where they're going to have to triage the scene, and there's going to be other times where they may not have the resources or budget to have something analyzed by a laboratory. I think that is a culture change that's going to be included into the use of RCAs, because if you don't know how something failed, you're just going to be guessing. And I'm sure the elephant in the room in a lot of RCAs is that they did an RCA and the part breaks again. And it's not that the work that was done was bad. It's just that they started off with the work started off with some very important assumptions, and those assumptions might be wrong. If you were given 3 more chain links, or let's say these 3 chain links, which have again all failed for very different reasons, you would be hard pressed to come back with a confident series of action items, especially if they're expensive action items that you're proposing, that's going to ensure that these don't fail again. And so that's it. I want to thank everyone for listening to me talk. And now the present day Shane will be happy to answer any of your questions. Thank you.
Let's get the point, and Bob Latino has 2 of them. Let's go to this one, please.
Hey everyone. I wanted to make sure everyone felt comfortable, so I made sure I wore the same shirt as the video, so that way it seemed like there's less of a time lapse in there. Hey Bob, great to see you. I'm a bad person here because I actually couldn't quite figure out how to answer your chats on the side. But so your first question, I believe here is great point. Appropriate. How could versus why questioning is critical to successful RCA? I guess that's not a question, but that's important. Okay. Do metallurgical labs typically assist their clients with why, or does the scope of work end with determining the how? Now, good question, and I think it comes down to each case a little bit differently. If first of all, you do want to get the how. You want to get the mechanism as to what caused it to fail: fatigue, brittle, corrosion-based, hydrogen, wear, high temperature, et cetera. Now, if the root cause turns out to be a quality issue with the broken part itself, it wasn't made properly, that's something that the laboratory should get closer to the why. But in other cases, they can only go so far, because in the end, it comes down to what information you get from the part. And my experience has been, if it's in some of the chain link examples I've had, you can't guess where the extra loading came from. So in the middle scenario, where you had, the first scenario where you had higher loading than the chain could sustain, you can only use speculation and say, hey, it makes sense that if you change the line 2 years ago, that maybe you increase the line tension or some of your bend radii after loading, but you're guessing. And that means you'll never fully get to the why. You can only help people and direct them towards the why. Bob, does that answer your question?
I think it did. And do you have any other, well, we don't have any other questions here, but do you have any more comments, and also maybe further to your book or anything else? We have a little bit more time, so.
Yeah, so I mean, I guess the biggest thing is that there's a few, perfect, good, Bob. Again, I think that never before has there really been an opportunity for other types of engineering to learn how to examine fractures. I know that when I was learning as a metallurgical engineer, 15, 20 years ago, there was really no books that taught how to do that. And so I think for the first time ever, I don't mean to make this sound like a plug, but I think for the first time ever, there's now an opportunity that people can actually, quickly read a book and learn the very basics to fatigue, to brittle, to ductile, and those are some of the more common failure modes that plants have. And then the other thing is that, you know, I hate to turn this into a sales pitch, but I mean, we're also offering courses that I think are relatively thorough, but I don't want to. I'll just stop there so I don't sound like I'm pitching.
And Shane, we got another question. I'm going to bring it up right now.
You know what? So that the RCA and RCFA is a reliability term. I actually think there's people who can answer that better. All I know is that people when they're first starting to investigate a failure is and the role that I play is in either of these cases is that they really do need to understand how a part failed. So I don't really think I'm the best person to answer that question. Are there any other questions?
Shane, thank you very much for your time. And that's it. And everybody, you guys know how to get in touch with Shane through the app. And Shane, have a great rest of your afternoon. Take care.
Thanks everyone for listening. Bye guys.